Hello, Professor Sargent here with you again. We're just going to take a look at one example here for the current material. We're going to build and analyze a function that's describing motion. We've got an island here where if you go straight, the shortest distance would be along a perpendicular. So 90-degree angle here. Going straight from the island to the shoreline is a distance of 12. And from that point P, where going straight from the island to the shoreline to the town, from point P to the town is 28 miles. We have a person who's able to row that 12 miles at 4 miles per hour. And the same person can run 10 miles per hour along the shoreline. Now, if they had not labeled this for us, we could have labeled X as the distance where the person lands from point P. They're not necessarily going to go straight from the island to the shore. They could go anywhere in between. So they could try to go straight from the island to town. They could go straight from the island to the shore or someplace in between. So I'm going to address the second part first, that the domain of the function t, which is going to be the time it takes t to complete that total trip from the island to the town. They want this in set builder notation as opposed to interval notation. So here it is in set builder. X could be 0 if we go straight from the island to point P. Therefore, we've gotten or equal to. And the highest it could be is 28 by going straight from the island to the town, not going to some place in between along the shore. Now, to come up with the function t of x, we're going to have to use the fact that the time spent is going to be a total of how much is spent rowing. So total time equals time rowing plus time jogging or running. And furthermore, we're going to have to use the uniform motion formula. If rate times time equals distance, r times t equals d, then time is equal to distance over rate. And so we're going to have the distance rowing over the rate of rowing plus the time running would be, that didn't quite work out nicely. So the time running would equal the distance run for over the rates of running. Notice that I called that the uniform motion formula instead of the distance formula. There's a reason for that we'll see in just a moment. So running and furthermore, we know that those rates are going to be the 4 miles per hour for rowing and the 10 miles per hour for running. Also, the distance that is run for. If X is the distance from point P to the landing point, then as we see in the diagram, we've got 28 minus X as the distance that the person would be running along the shore. And by the way, you could think of this as being kind of like, say, part of the Ironman triathlon, the swimming portion and the running portion. They've left out the bicycling portion to make it a triathlon. Let's see here. So I've created my own version of the question. So, but real quick, I'm taking a look at how they print the answer in the similar question on our homework. So give me a moment on that. So the reason that I didn't call D equals R times T the distance formula, I call it the uniform motion formula. We're assuming the same rates the whole time. I did that because we're going to have to use the distance formula that's related to the Pythagorean theorem to express the what do you call it? The distance that is rowed for. So I mentioned that we've got a right angle at point P. This triangle where I'm moving the mouse around is a right triangle. And if we apply the distance formula, then we're going to have that the distance rowed for is the square roots of x squared plus 12 squared. And 12 squared is 144. So let me get that typed in a moment. Okay, so I've got that typed in there. Now, regardless of what you put in for x, you're going to get under that square root, x squared is going to be at least as big as 0. Adding 144, you're going to get something at least as big as 144 under the square roots. And so when you apply the square root, that's at least as big as 12. Dividing by 4, that first fraction is going to be at least as big as 3. But if you put in something larger than 28, then this part's going to be negative. So that won't make any sense for the time spent running. And if we put in something smaller than 0, although you would get a positive and the whole thing would be positive, that's irrelevant because the time spent running could not be negative. Now, I've already put in what that domain is. Oh, I forgot to close off the set builder notation. There we go. Remember, that's in set builder notation, not interval notation. Now we're looking for writing this as a function of x based on the distance of the landing points from point P. So there it is written as a function of x. And we're asking these last two parts to approximate to the nearest tenth. How long is it going to take if the person lands 12 miles from point P? So we're looking for t of 12. By the way, there's nothing we could really do to simplify that formula. Put in 12 for t. And over here as well. It's going to give us 104 plus 144 for a square root of 288 divided by 4. Then 16 over 10, that's going to be 1.6. So I'm getting approximately, let me show you everything the calculator is giving, followed by rounding it to the hundredths place, which is 2 places out. Try that again. I wanted to get the approximately equal sign to show up there. And it's not agreeing with me. So although that's not the approximately equal sign, there should be 2 of those little squigglies to make a curvy equal sign instead of an exactly equal sign. I'm getting 5.84 to 5.84 to 2 6 40687, and that will round to 2 places. It's going to round, darn it, that was a 84. So that's going to round down to 5.84. 5.84. Getting used to a new keyboard here. Considering that our distances were in miles and our rates are in miles per hour, then this must be approximately 5.84 hours. And I'm curious, in this last part, if the person lands a little further away from point P, here we had 12 miles. Now what if they land 14 miles away, which would in fact be the halfway points? Then what's that going to do? Does that increase the time? Does it decrease the time? Does it make it stay the same? So we're looking for T of 14. 14 squared plus 144 is still under the square roots. And let's see what happens. 14 squared, I think that's 196. Yes, add the 144. We've got 340. Take its square roots, 18 point something. Divide by 4, that's 4.6 something. And we're going to be adding 14 over 10, so 1.4. I'm actually getting something larger this time. The entire thing I'm coming up with is 6.00977 2229. And rounding that to the hundredths place, this one's going to round up to 6.01 hours. That's all for now. It's not an entire playlist for this one, just one question. If this has helped, press the like button, subscribe to the channel, and if you know somebody working on a similar problem needs help, share it with them. And I will see you next time. Have a good one.